Go.
Okay, is this thing on? Perfect. Okay, and I assume there are some slides that should be coming up at any moment now, I assume. Otherwise, I can do some stand-up, but I don't know how much you will enjoy all of this.
1 second.
You know, free cryptographer enter into a bar. I only know the one about the mathematicians. The one about the cryptographer is computationally hidden.
So maybe while it's starting, give us the overview of what you're going to be talking about.
Okay, yeah, so today I'm going to be talking about this new proof system that we have, WHIR, which from maybe a slightly biased opinion I find pretty cool. So roughly the replacement for like, okay, perfect. The replacement for a common protocol, which is the FRI protocol, and an improvement on our previous replacement of the FRI protocol, the STIR protocol, which promises to just reduce basically proof size, verification size, and recursion overhead.
So where you will need to tell people to slide the slide next.
Ah, okay, so I cannot use the beautiful pointer.
Maybe, I don't know, but let's try.
Okay, I'll let them, because I couldn't figure out how to use the Google Slides, so this was like my, this PDF was my alternative for this.
No problem.
Okay, so I guess we can start. Okay, so yeah, WHIR. So this is joint work with Alessandro Chiesa, Elon Yogev, which are both here, and Gal Arnon, which is here with us in spirit, is actually doing very extremely well, it's just not here physically. So WHIR is this proximity testing for Rich-Solomon code. And in fact, the plus over here is that we're not going to be actually proximity testing for Rich-Solomon codes, but actually for something that we're going to be, that I call constraint codes, which I'll tell you why you should care about them. So next slide. So let me start with some motivation. Next slide. So we care about constructing IOPs. Now it works? Okay. I don't believe it does. Okay, I'll tell you. Okay, so we want to construct IOPs. Why do we want? What are IOPs? First, they're like these. They're these interactive protocols between a prover and a verifier, in which a prover sends you some oracle strings, and the verifier can make like queries to these strings. And the reason why we want to construct these IOPs is because they help us into constructing succinct arguments. Later on, you can compile them with something called the BCS transform to achieve very efficient arguments. So now it works. Ah, beautiful, amazing. Oh, thank you. Okay. Thank you. No, I have to say I made it hard for the organizer, so this is yes. This was an adversarial talk, funnily enough. So, okay, I like compilers. I think abstraction barriers are very good as a way to think about things. So, to construct these IOPs, we're going to be like actually moving things a step back. We're going to be constructing something conceptually simpler. And this is a polynomial IOP. So, these are again also interactive protocols in which you have prover and verifier which interact, and the prover sends polynomials, really polynomials to the verifier, which then can query the evaluations of like these polynomials at points of its choosing. Now you want to compile these kind of things into an IOP. And the strategy that you end up doing is that you want, which is very efficient, is to actually use error-correcting code as your building block. So the way that most modern star constructions are done nowadays is by actually using this Rich-Solomon code as a source of redundancy, and then use something which is called the proximity test, which we'll see in the next slide, to check claims of the encoded oracle. So when I compile things, I'll just have my IOP in which the prover runs internally the prover of the polynomial IOP. This gives you a polynomial. You send it over as this Rich-Solomon encoding, which I'll explain what it is later on. And then the verifier will run the verifier of the polynomial IOP, and when the verifier wants to query f at the point z, well, the prover will just give it the actual point. Now, of course, we're not in the business of trusting provers, so we want to keep the prover honest in actually sending a value y, which is consistent with the polynomial it has committed to. So the way that we enforce this consistency by doing this Reed-Solomon proximity test on a virtual function on this quotient. And for this talk, it doesn't really matter what it is, but this is how most of the efficient star contractions are done in practice nowadays. And the argument size of this construction almost directly and almost entirely depends from this proximity test. Okay, what are these proximity tests? Well, so first, let me recall what are Reed-Solomon codes. So Reed-Solomon codes are just evaluation of low-degree polynomials. So I'm taking a polynomial of 2 to the m coefficients, and then I'm writing it down on a domain of size n. And one notion that we're going to be interested about this encoding is the rate. So this is how much larger the evaluation domain in which I'm writing down is compared to the coefficient of the polynomial. So in an IOP for a Reed-Solomon code, what you end up having, you have, again, an interactive protocol between a prover and a verifier. The mode of interaction is the same as an IOP. So the prover is allowed to send these oracle strings, and then the verifier can query them. And additionally, the verifier and the prover have access to this oracle, this f in the sky. And the kind of 2 functional properties that we want to have is that, first, if this oracle in the sky really is a Reed-Solomon encoding, so really it is the evaluation of a low-degree polynomial, then the verifier will be convinced by this interaction, while later on, if the function is far from Reed-Solomon code, the verifier will only accept with small probability. And this soundness notion, which is not really soundness, this is proximity, is what the IOP proximity takes the name from. So the reason why we have to give this weaker guarantee is because we don't want to read the entire function. So we can only query it at a few places, and the fewer queries that we make, the more efficient our proof system will be. Okay, so we're going to be looking at how to construct this primitive, this IOP proximity, but not exactly the IOP proximity for Reed-Solomon codes. And yes, we also achieve a notion of round soundness, which is required to be able to compile the protocol successfully. So, in fact, we're going to be looking at something slightly different, which is this constrained Reed-Solomon test. So, recall that in this kind of like blueprint that I gave you before, we're running this Reed-Solomon proximity test. But really, the reason why we want to do this is to show that there's some polynomial that we have committed to, such that it evaluates to y at z. So this is the reason why we're doing it. So conceptually, you can break this. You can break down this proximity test as 2 steps, really. One is first taking the function and turning it into a function which embeds the constraints inside, and then later on proximity testing this new function, this virtual function. And these are the old slides. And the reason why we really care about this proximity test, we care about it for a lot of reasons, but for the purposes of this construction, we want to check this constraint. So this naturally leads to a question like, why are we doing this step in which we have to do two moves? Let's just make the proximity test directly test the constraint. So can we move this constraint checking directly into the IOPP? So we look again at our Reed-Solomon codes, and in this talk we're going to want to extend the functionality as well, so we want to talk about multilinear polynomials. So I'm just going to rewrite Reed-Solomon code to be about multilinear polynomial. Roughly this just ends up evaluating the multilinear polynomial on a funny domain. Don't worry too much about it. But now I'm going to extend the Reed-Solomon code by adding a constraint on it. So in this case, this constraint is given by these 2 values, this weight polynomial and the target, which is the value of the constraint. So roughly now my new code contains of is the same as the Reed-Solomon code, but additionally I want some constraint to hold. In this case, these are like sum check constraint because, spoiler alert, is a ZK talk. We're going to do sum check at one point. Not in particular, this is general enough to actually capture the Reed-Solomon codes that we know and love. And in particular, if like this weight polynomial has this particular form, we're actually able to recover multilinear polynomial evaluation, which is something that we actually care deeply about. So this is, under our blueprint, we want to construct something for this contrary Solomon code, which I'll later tell you that ends up like being a good thing. So what are our results? Well, we construct WHIR. So WHIR is exactly an IOPP for this constraint with Solomon code. So it's an IOPP which tackles exactly this problem. So it has, like, let me tell you, it has some properties that we call query efficiency. In particular, the number of queries in the parameter regime that we care about ends up being exactly O of lambda, which is asymptotically optimal for like these kind of IOPPs. In particular, we care of a setting, and these asymptotics assume that the security parameter is much larger than your like instance size, and we set this folding parameter to this. I fucked this presentation. That to like to be around log of n. Further, we show that this constraint with Solomon proximity test end up like being a useful notion. So we show a nice soundness compiler that takes any generalized notion of a polynomial IOP, which we call sigma IOP, compiles it with a constraint with Solomon IOPP to get an IOP. And this is an analog to the rich Solomon polynomial IOP compiler, which uses quotients. Further, we have an implementation which is decently written for like academic standards. So, you know, doesn't really say much, but it's pretty nice. Okay, so just to compare with previous works, here are like just some slides. Roughly compared to like works as Fry and Basefold, we get like exponential improvement in the query complexity. And compared to work like Stir, which also achieved this exponential improvement in the query complexity, we end up getting a much better like verifier asymptotic complexity. So further, like WHIR acts directly as a replacement for Fry and Stir. This is given by the fact that the constraint with Solomon codes end up like generalizing with Solomon codes. It has the same benefits as Stir over Fry, so the reduced queries and the reduced recursion overhead, and a similar prover time. Additionally, it is a richer proximity test. So while Stir and Fry ended up being very natively about univariate polynomials, like WHIR can be used for multilinear PCSs. So it can be used to compile polynomial IOPs which deal with multilinear polynomials. So it can also be additionally used for these sigma IOPs, which I'm going to be maybe talking at the end, depending on time. And further, the asymptotic improvement in the verifier complexity leads us to a notion which we call superfast verification, which I'm going to be talking next by just showing you the numbers. So the WHIR verifier runs in a few hundred microseconds. So every other verifier known in the literature requires several milliseconds and more. And this is all without compromising on prover time and argument size. So just to give you some numbers, so like as a polynomial commitment scheme for degree 2 to the 24 and 100 bits of security, the prover time is around 3 seconds, the proof size is around 70 kilobytes, and the verifier time is around 300 microseconds. To give you some point of comparison to other things known in the literature, like here I put like every polynomial commitment I could make run on my laptop. I put it there, and like there are other hash-based schemes, like for example Breakdown, Ligero, which are they're not succinct, but and so they have verification which is on the order of seconds, let's say. There's some lattice stuff like Greyhound, which is in order of like 0.1 seconds. Then there are IRATs, PST, and KCG. These are elliptic curve schemes. And they also have around 100 milliseconds, 7 milliseconds, 2 milliseconds, where instead consistently I manages to achieve a verification size of around a millisecond or below. And what I want to point out in this comparison is that like PST and KCG are both schemes using elliptic curve with trusted setup using pairing, while WHIR inherits some of the features of like hash-based polynomial commitment schemes in that it has no trusted setup, it has a transparent setup, and it is plausibly post-quantum secure, in that is the only cryptographic assumption that it requires is the security of hash functions, or really the random oracle model, which we have talked about a bit today. So I don't know how much I will be doing with time, but let me start to diving in some of the techniques of what WHIR ends up doing. So as a review, we're going to be talking about the fry and stir folding. So this is the core component of basically all IOPPs for rich Solomon codes. So we are in the business of trying to reduce the size of problems. And folding is a way that you can take like some, so it's a way which you can take like some code word of some size and try to reduce it. Roughly, these are like some protocol between a prover and a verifier, in which the verifier samples some randomness, and the prover and the randomness will define some fold, which ends up like being, in the honest case, a code word of a dimension which diminishes by 2 to the k. And the way that you can think about it is very similar to an FFT, so you can think of taking the odd and even coefficient of the polynomial and just taking a random linear combination of them. And this fold has a lot of properties, but roughly for soundness, the most important one is that of distance preservation. Namely, if you end up like taking this, if you end up taking a function which is delta far from the code, and then you fold it, then unless with some small probability, the fraction of corrupted entries will not decrease. And this leads from a very beautiful result, which is called the proximity gap for Solomon codes. So this is not enough for WHIR. So in WHIR, later on, we will not see because of time, but what you will be wanting, you will want to handle constraints. So we want to test proximity of constraint codes. And we will want to give like this kind of, to fold at the same time both the constraint and the code word. So it turns out that just created agreement in itself is not sufficient, at least in the regime of list decoding where we are like interested on. So we want to introduce something different that is strong enough for our notion. This is mutual correlated agreement. So, okay, suppose that we have m function that we want to test proximity to. Of course, having m function to test is very cumbersome, so we might want to reduce them to a single one. So the way that this is done is via the only trick that we know, which is a random linear combination. So there's a long line of work which tries to decide what a test on f star tells you about the function that you originally randomly linear combined. So if, for example, the final function is close to the code in some like portion, which I put here in green, like the agreement theorem tells you that like all the other function will also be close to a code in some portion. Correlated agreements strengthen this and say like, look, the picture it doesn't look like this. In reality, all the function end up like agreeing with the code on the same stripe. Of course, if you look at this picture, this is, a bit annoying because you have all the stripes on like one side, but the stripe of the thing that you've tested is on a different stripe. So you might say like, look, there's no reason in the world why this happens. And in the picture that we should really be looking at should be this. So the mutual correlated agreement should be all on the same stripe. And this is what we stated happens. And this can be thought about that taking a random linear combination does not create new agreement domains. So why is this notion nice? And I think this we'll see how we do with time. So this the fact that this mutual correlated agreement gives you rise to some very categoric theoretical kind of like interpretations. Roughly, you can think of like taking a list of functions, taking a random linear combination of them, and taking a list around the random linear combination. Well, what mutual correlated agreement tells you is that you can go this way in this diagram, or you can alternatively, this is the list, or you can alternatively take the list of the interleaved code around the function, then take the random linear combination of things of the list, and then you arrive at the same stop pot. So this diagram ends up commuting. So this is what it's how you can write it formally. So the way they like to think is that each term in the left-hand side can be explained by terms in the right-hand side. So in the paper, we show that the correlated agreement implies mutual correlated agreement in unique decoding. We do not know whether this holds in general, and in fact, I think it's a very exciting question to work on. But luckily, we're kind of been vindicated in the fact that this notion has been shown to hold for general linear codes up to the 1.5 Johnson bound. So the people are the mutual correlated agreements end up like being at least somewhat of a natural notion for codes. So, am I doing for time? Should I wrap up? Are we?
1 minute, thanks.
1 minute, okay. So maybe I'll go with my favorite slide, which is the WHIR iteration. So WHIR ends up like being the following protocol. So we remember what we're doing. We want to test a constraint with Solomon code. What we do, we start and we run k rounds of sum check. So this ends up sending sum check polynomials. Then the sum check randomness defines the folding of the function, and the prover sends a re-encoding of G under a different rate, a code of a different rate. So this is on a domain larger than what the fold will be. Then these are claimed to be the same polynomial, but we don't really have, we cannot trust the prover for having sent the same polynomial, so we need to have some consistency in order to hold the prover accountable. And what happens that we do is we end up doing this protocol, which is called a domain shift, which I don't have time to talk about, which ends up making T queries to the original function, and it will return a list of claims on G, the new function. Then these claims end up being batched into a single claim, and then we recurse on this protocol. So this is a very similar structure to stir, but now we're working like in this multilinear world. And quotients that were very successful using stir just do not end up giving you any mileage in the multilinear world because things end up just breaking. So we need new ideas to domain shift, which I will not have time for that, but I have a beautiful slide at the end with an ePrint.
Go ahead with the domain shift, and then we move.
Sorry,
to
and
it's too
no. Like, look, I think I'm not a terrible speaker, but I'm not that good.
Okay.
Okay, so this is a sigma IOP, which is.
Yeah, so can I prompt you with in conclusion?
Yes, that's a conclusion slide. So.
Thanks.
There's the ePrint. There you can look a lot about the domain shift. I have these full slides up somewhere. But roughly the point I want to make is that WHIR ends up like giving you a state-of-the-art hash-based argument in terms of argument size, hash complexity, and it has the fastest verification of any polynomial commitment scheme, including pre-quantum one, which make use of trusted setups. Furthermore, it enables new construction of a generalization of polynomial IOP, and enables high-soundness compilation for these new sigma IOPs. So this has been my time, and yeah, WHIR.
So thank you so much. I have one question for you. So we know about STIR, we know about WHIR. Is your bet on evolutions again on these for the one that will take us for the third millennia, or? So
predicting the future is notoriously hard. So what I will say is that stir, WHIR, fry, they end up like constructing argument via pattern, which is by taking some information theoretical components like this polynomial IOP and then connecting it with some proximity for some proximity test. Now, proximity test in general, there's a limit to efficient they can be. There are like some error terms which end up like appearing, which kind of limit you to how small the argument size can be. So you can improve on things, but up only to a point. Now, is it so? On that, if you look at it asymptotically, like WHIR is as good as possible. So what you can improve is in constants, but this can be they could be very concrete things. I think I was doing some back of the envelope. There's like a 2x that you can get in argument size probably. Now there's a state. Does the state of the argument of the universe allow you to go as low as the limit? That I have no idea. So I'm saying like this is a very exciting area of research, and driving down argument size is due to lead to the most efficient arguments known, and whether you can get better than this from like different techniques rather than just some parameterization, that's a very exciting open question.
Amazing. Thank you so much.
Thank you.